It's been a while, but we are back. Hello everyone and welcome to Tech Talk. In our Tech Talk series, we speak with different product and application experts from IPG Automotive to get insights into various innovations and trends from the automotive industry. Today, my colleague Martin Herrmann is joining me. He is a business development manager with a focus on ADAS and AV development. Martin, it's great to have you here.
Hi Anna, thank you. It's my pleasure.
There is a reason that you are our guest on Tech Talk today. This time our topic is sensor simulation, a pretty big topic in ADAS and AV development. So you are exactly who we need to talk to today. But before we dive into this very interesting topic, tell us more about your field of work.
Yes, Anna, of course. As I work in the area of ADAS and automated driving, I work with our customers and partners on simulation-based solutions for testing these kinds of functions. So, as you already have mentioned, sensor simulations is a pretty hot topic in the industry right now, as perception is a big challenge for autonomous cars. So, simulation is becoming increasingly important. Synthetic sensor data can be used during development processes as additional training data for AI perception, but also for testing these kinds of sensor software and the sensor components.
Before we get into more detail, which types of sensors are the most relevant for environmental perception and how are they used in simulation?
Yeah, the typical sensor technologies for autonomous driving are camera, radar, LiDAR and ultrasonic sensors. Each of these sensors can be simulated in various levels of granularity, depending on what is the purpose of the simulation and which kind of system or function is tested or developed.
What are the different use cases?
The main question you have to ask before choosing a certain simulation model is, do I really want to include the perception software in my test setup, or do I want to test the planning and motion control part on its own? This makes a huge difference both for sensor and environmental modeling effort. We call it purpose-driven fidelity. If I am an OEM and buy one or more sensors for an ADAS function, I typically have no know-how about the perception software. It's usually built into the sensor or function ECUs themselves and delivered by the Tier 1. So I need a rather abstract model delivering an object list, either ideal or some modeled phenomena, resulting in false positives and false negatives and noise on the object list.
And what if the customer really wants to focus on the perception software?
Then the sensor raw data needs to be simulated. In CarMaker, we have a module called Physical Sensor Models, which can generate camera images, radar detections, or LiDAR point clouds based on sophisticated models using rendering or ray tracing technology. We could probably talk an hour about each individual sensor technology and how they are modeled to generate the raw signals. But to make it short, there are models to take care of the signal propagation in the 3D scene, considering environmental effects and material properties. There are models for the sensor hardware, such as images or radar antennas, and depending on the sensor technology, some basic pre-processing. As the signals are dependent on the 3D scene, GPU power is necessary to generate the sensor data, and depending on the required fidelity, quite a lot could be required. Here our Sense Compute platform can help. It has multiple GPUs and is our standard computing platform for complex sensor setups in ADAS and autonomous driving.
Yes, in a minute we are going to have a closer look at the platform in the demo. But first let me ask you this. Once the data is generated, how do I transfer it to my perception software?
Again, this depends on the setup you have. So if you are in a pure virtual environment or if you want to simulate in a real-time context. For software-in-the-loop applications, we can directly provide the raw sensor data using the raw signal data stream, short RSDS, which is our data protocol to exchange sensor data between various applications. In real-time environments like hardware or vehicle-in-the-loop with real ECUs, such as sensor ECUs or central AD processors, we can inject the raw sensor data into the ECU with our Sense Inject platform using industry standard formats and interfaces like GMSL or Automotive Ethernet. We have prepared a hardware-in-the-loop demonstration using both Sense Compute and Sense Inject where I explain the whole process in more detail.
Sounds great. Let's take a look. Well, that is quite a setup that we have here with many different factors to take into account. Could you explain how the setup works and which functions each of the components have?
Yeah, for sure. We basically have two monitors here. On the right side we see the CarMaker user interface together with a visualization of our test scenario. The user interface is running on the host PC inside the black box. And this one is connected to our XPAC4 road box where the actual scenario simulation happens, and also the vehicle dynamics simulation and the I/O generation for our system under test, so CAN communication basically. Then the sense compute is calculating the radar raw signals, which are processed by our sense inject and injected into the system under test on the very right side. What's happening on the system under test is visualized on the second monitor, where we see the radar raw detections and also the outputs of the sensor fusion, so the tracked objects over time.
Could you show us an example to see how it actually works?
Yeah, for sure. We have prepared a typical highway scenario. We have a car equipped with an advanced cruise control function, and it is approaching a few other vehicles, and one of them is cutting in front of us, and the system has to decelerate because it's getting very close to this object, and then when the object is further away, it can accelerate again. So the input to that ACC is an object list, and this needs to be generated by our system under test, and we see that on the left side. So in red we have the radar raw detections, then in gray, so these small gray arrows, these are the unconfirmed objects, so a potential detected object. And in light blue, we see the actual confirmed objects, the tracked objects, and we can directly compare them with the ground truth shown with the yellow boxes, so we directly see how well the perception itself is working. And then the generated object list is injected into the motion planning and motion control part of the function, so that we actually have a full closed loop simulation of this real ADAS ECU in the loop. And the general setup is empowered by our XPAC4 real-time platform, our sense compute to generate the sensor raw signals, and the sense inject platform for injection into any ECU in the loop.
That was a very helpful example. Thanks for showing us, Martin.
You're very welcome.
To sum it up, who do you think may benefit the most from this technology when developing ADAS and AV functions?
Well, the Sense Compute platform can serve perception developers who just need to generate vast amounts of synthetic training data, as well as perception software and hardware testers, as they also need the synthetic data as an input. Of course, also for full system test and validation, the Sense Compute can take care of generating the sensor inputs efficiently to enable closed-loop testing. As soon as there's a real ECU involved, the Sense Inject takes care of the signal conditioning and injection of the data into the device under test in a real-time environment.
Let's take a look at the future. What do you think? How will ADAS and AD development, as well as sensor simulation, impact the automotive industry going forward?
The most exciting thing for me to see is how sensor simulation is adopted in productive development processes. With recent developments in physical sensor simulation, we have enabled the simulation of complex sensor suites for autonomous vehicles, and this is necessary for full system validation. But there is more to the overall development process. The other sensor model classes, ideal and phenomenological sensors, still have their place, and they are very efficient for unit testing and of the planning and motion control function. And they require a lot less effort when it comes to scenario modeling. So it will be interesting to see how the two fundamentally different simulation technologies develop and to what extent they will be used in the future.
It seems like there is a lot of work in the industry. Thank you, Martin, for your detailed insights into this specific application field today. And I hope we can look at other aspects of automotive sensors someday, maybe in this format again.
Yeah, thank you, Anna, for having me here today. It was a great chat, and I hope I was able to give a few insights our viewers can also benefit from in their own development processes. For sure, if anybody has further questions about this topic, I'm happy to help.
You heard it. Feel free to contact Martin directly via email if you have any questions about this topic. As always, I hope you enjoyed this Tech Talk, and I can't wait to see you next time. Bye!